Hello friends, so today we're going to discuss a very interesting problem from AtCoder Beginner Contest 120, Problem D, Decayed Bridges. So I first tell you that through this problem I'm going to explain the data structure union find. It is a very interesting data structure and we're going to learn how to implement it using this question. Cool. So you are given n island and m bridges. Okay, the ith bridge connects the AI and BI island bidirectionally. So there are like n islands and m bridges, and there is a bridge from AI to BI. It will connect these two islands. Now you can travel between any two islands initially from any bridge. However, the result of the survey shows that the bridge will all collapse because of aging in the order given in the mth bridge. So this first bridge will collapse and the second bridge will collapse and so on. And the inconvenience is the number of pair of islands such that there is no longer a way to travel between the 8th and 8th island using some of the bridge remaining. Okay, so like let's say there are two islands and you cannot travel between the first island and the 5th island. So there will be an inconvenience between them. So you have to find out the number of pairs. How many inconveniences are there when the ith bridge collapse? Okay, so you have to find out the inconveniences for every bridge collapse. So as you can see, there are like 4 islands and 5 bridges. These are the 5 bridges. When they collapse, what are the inconveniences? So when the first bridge collapses, there is no inconvenience. Second is no inconvenience. But if the last bridge will collapse, nothing is connected. So there is inconvenience of 6. Okay, so I'll tell you how, and we're gonna discuss the data structure also through this question. Okay. So first we're gonna see this question and then we're gonna discuss the data structure. Okay, so this is the question. Let's assume these are the 4 islands. Okay, and we're gonna connect them also. How they are connected? 1, 2, 3, 4. 1, 2 is connected. 3, 4 is connected. And 1, 3, 2, 3. So 1, 3 is connected, 2, 3 is connected. And also I think so 1, 4 is connected, and 1, 4 is connected. So you can connect this like this. Okay. So these are the connections, and so this is the last one to fall. When this one falls, or they actually fall in the start order. 1, 2 will fall first. When 1, 2 will falls, still there is a way to go from 1 till 2, and thus there is no inconvenience. As you can see, if I delete this, then again there is no bridge directly from 1 to 2, but I can go from 1 to 2 in this way also. Okay, so there is some path, but the inconvenience is if you cannot reach any island by any way. So if you in the simplest way, what you can do, after each bridge collapse, you can take out that edge and then run a BFS and see whether there is a path, the shortest path. There exists some path from one node to another, but that's a very long and it will time out. But in such questions, if you cannot go from ith bridge to the last bridge, what you can do here is you can assume that there is initially no bridge, because you will go not from the start to the end. You will not break out bridges at every point, but you will build bridges. Okay, so what does this mean? It means that you are given n islands and you will connect them one by one, and you will check that after this connection, what are the possible what are the islands which will be reached after this connection. Okay, so let's assume that in the end, as you can see, there is a connection between 1 to 4. So in the end, it means that if I connect 1 to 4, these two islands will be reached. Okay, initially there is no island to be reached, and thus what is the inconvenience? Inconvenience is n into n minus 1 divided by 2, because for every island I cannot reach the other islands. Okay, so it is just n into n minus 1 divided by 2. Why? Because for every n island I cannot reach the n minus 1 islands. Okay, and you will divide by 2, and then this is the starting inconvenience when there is no bridge at all. Okay, so as you can see, it is 4 into 3 divided by 2, which is just 6. Okay, so that's the first value, and this is the last value, which means that when there is no bridge, when now we start building bridge, and it means that when we build this bridge, you can reach between these two cities, and thus there is one convenience down, because you can reach from 1 till 4, but you cannot reach from 1 till 2 or 3, so there is just one inconvenience down, so the answer will be 5. Okay, and so on. So as you can see, now we are forming components. As you can see, this is one component now. Now the second is you can link 2 and 3. Now if when you link 2 and 3, it is forming some another component. And as you can see, now these two can be reached, but these two still cannot be reached. And thus there is only one way also down. So there is 5 now, then it will be 4. Okay. Now you will link 1 and 3. Now when you link 1 and 3, what will happen? When you link these two components, this component is different and this component is different. When you link these two components, then what will happen? Every city of this component can be reached to every city of this component. Okay, so as you can see, I can reach to every city of this component can be reached to every city of this component, and thus the size of this component into the size of this component, because as you can see, the size of this component is 2 and the size of this component is 2, which is equal to 4, and thus there is an increment of 4 more pairs which can be reached after this connection. Okay, I hope you understand. And thus as you can see, it is just when you do, because there is 4 more components, you subtract 4 more from this, and thus it will become 0. It means that now everything can be reached. And then after, like, again, if you add one more component, like as if you add a bridge from 1 to 2, now as you can see, after adding this bridge, the components are still connected. You are not adding a new component to this structure, and thus the answer will not increase. So these functionality will be like done easily using the data structure union find. So what union find build does is that it will take some components and it will help us to find some queries in which you can find out the size of the component easily, and also you can connect two components easily. And you can, if you are given two nodes, like if I am given 4 and 3, so in the initial state such that if there is a stage such like this, okay, I'll go back. If in this stage, if I want to find out what is whether 4 and 2 are in the same component or not, it can be easily find using the union find data structure. If I connect now, what you can do, you can connect these two nodes, and then you can unite these two components using some function in the data structure union find, and then when both of them got connected, you can again find out what is the whether the node 1 and 4 belong to the same component. If they belong to the same component, then yes, like you can find out these queries in O of 1, like almost O of 1 type, amortized O of 1. So that's the whole trick for using union find. So I'll tell you how we implement union find. So union find, what it does, it will take care of two arrays. One is the size and one is the parent. Okay, one is parent, I'll denote it by P, and another is size, which I denoted by SZ. Okay, so let's assume that you have 4 nodes initially. I'll clear out this part to make it more clear. So let's assume you have 4 nodes initially. Okay, and so what you will does, these are numbered from 1, 2, 3 and 4. I'm explaining how union find works. 3 and 4. Okay, now because nothing is connected initially, everything is the parent of itself. Parent means parents help us to find out the connections or the component. Okay, we're gonna understand more in the later video. So as you can see, first every node is just the parent of itself. As you can see, now everything is the parent of itself. So this is the parent. This array stores who is the parent of which. So for 1, 2, 3, the parent of like 1 is 1 itself, 2 is 2 itself, 3 is 3 itself, and for 4 it's 4 itself. Okay, now the size of every component is 1 initially for all these things. Okay, now what you can easily find out is like if I want to do some unite, I want to join these two. Okay, first I want to see that whether if I want a query such that join 2 node and the third node, first I want to check that whether 2 and 3 are already connected. If they are already connected, like there is no need to join them. Okay, but if they are not already connected, we have to join them. And then what we will do, we will make either two, like we will either make this, because it is telling that the parent of 2 is 3, we can either make this arrow turns to 3, or they can also like do this, I can make this 3 turns to 2. But it is generally a good practice that you can, if you have to combine two components, then the one component which has the larger size and one component if it has a smaller size, then the smaller size should be combined to the larger component. Okay, so let's assume like they have like this component is connected to this component, and like this component is connected to this component. Now if I want to add this component to this whole component, then it is beneficial to add this component to this component, not the other way around. Okay, so now if I connect these components together, if I want to connect 2 to 3, then what I have to do here is, so as you can see, because the size of both of them are same, I can connect anything to anything, anyone to anyone. So in this I connect 2 to 3, or like 3 to 2, the parent of 3 now becomes equal to 2. So the parent of 3 now becomes equal to 2. So I have to do this. And this is how the modification is done. Okay, now what you can easily see here is the size is also incremented. The size, and now 2 is the parent. Okay, so now if I want to check that whether 3 and 4 belong to the same component, then how we will check? For every node we will go till its parent. Okay, because if we go till its parent help us to know the whole component, because everything will be pointed out to its parent. Okay, so let's assume we want to check that whether 3 and 4 connected comes to the same component. So what we'll do, we will move from 3 to its parent, which is 2, and we will move from 4 to its parent, which is actually 4. And if they are not same, like they don't belong to the same component, and then we can actually like combine them. So now we have seen that, and also we have to increment, because we have joined this component to with this component. We have to see what is the size of this component. It's 1. What is the size of this component? Like 1. So we will add the size of this component to this component. What is the size of this component? It's because this is the parent. So parent stores the size of the whole component itself, and thus because 3 is the parent, we will add the size of the parent to this node, which is because 3 stores the size of this, we'll add 1 to this position and it will becomes 2. It tells us that there is a node which is a parent, and it is a component, and it has a size of 2. Now if you want to combine 1 to this component, what we will do, we will check that whether, so if we want to combine 1 and 3, let's say we want to combine 1 and 3, so we will not directly make like combine this, we will not make like 1 a parent of 3. No, we will find out what is the parent of 3 and what is the parent of 1. The parent of 1 is 1, the parent of 3 is 2. So we will combine and we will check who has the larger size. Because 2 has the larger size in compared to 1. So it is beneficial to match, or we will join 1 to this, the smaller component to the larger component. And when we join this, we will add the size of this component, which is 1, to this whole component, which is 3. And then what we will also do, the parent of 1 becomes equal to 2, and we will make this. So that's how we will join the two components. Okay, now if you want to check that whether if two components belong to the same component, we can easily check also. We will just go to their parents, because if you want to check like whether 1 and 3 belong to the same component, we will just go to the parent of 3. And how we can go to the parent? We can recursively call this function p, or the parent function, because for the parent it is actually the parent of itself. For 2 is the only node in this, as you can see, except 4 also, but 2 is the thing. if you want to start with 2, we will check that whether 3 is equal to 2. No. So it means that 2 is the parent of 3. So we will go to 2. Now we will check that 2 is equal to 2. Yes. It means that 2 is the parent of itself, and thus it means that 2 is the ultimate parent of this component. And we will do same for 1 and 3. If you want to find out whether 1 and 3 belongs to the same component, we will go to its parent and check whether the parents is same. Yes. So it means that they belong to the same component. Now coming back to the problem, because we have connected two islands, we will check that whether they belong to the same component. If they belong to the same component, then adding them will not be beneficial, because it will not be incrementing some like pairs. But if we add two components which are not like initially connected, if we add two components, then the total number of islands which will be connected after this connection will be equal to the multiplication of the size of the first component into the size of the second component. And that's the whole logic of this whole question. I'll take down to the code part to make it more clear. So that's the solve function. That's answer, which stores the answer of all the like how many inconveniences there. We will, okay, so what we'll do, I'll tell you first this. So because there are m islands and m connections, for all the m islands, what we'll do, we'll mark the island or nodes actually, or island will the parent of every I is I itself, and the size is initialized to 1. I hope you understand. I've told you every island, the component is size is 1 and the parent is itself. Then we will store for the bridge connections. Okay, I have stored this minus because for the indexing one, because indexing is from 1 there and I want to do the indexing from 0. Then because initially there is no connections, and thus for the last bridge the total number of inconvenience is just n into n minus 1 divided by 2. Then we go from back to start, in which we start building these bridges. And what we'll do, we will check that. So we will, when we build a connection from x to y, we will check that whether they belong to the same component. If they belong to the same component x and y, then like the inconvenience doesn't change, because they belong to the same component. There is no increment in the connections, and thus the answer of I is just the answer of I plus 1, which we have earlier calculated, because there is no change. Else what we will do, because now they don't belong to the same component, what we'll do, we'll first find out the size of each component. Okay, the size of the each component we want to combine. Size of the each component is size of x is, we want to find out the size of x. We want to find out the size of the parent, because parent store the size of the whole component. So what we'll do, we'll find out so this is actually finding out the parent of x and finding out the parent of y, and just finding out the size of that parent, which stores the whole component size. And we will join x and y, and the answer is just, we will subtract answer of I plus 1, because answer of I plus 1 stores the whole connections, and if we subtract these new connections, it will tell us how many new connections have added due to this connection. We will minus this new connection from the total connections, and we will answer out the maximum of all of them, because we don't want to go below 0, and we will just output all the all the connections. Okay, how many inconvenience will be there from 1 to m. So we are just moving from back to front. Okay, now we're going to discuss how these functions are written. So we have stored the size and the parent. This is the vector for storing all the bridges. Now finding the component, whether x and y belong to the same component. I have checked that. So how we can check whether they belong to the same component? We will just go to their parent. If the parent of x is equal to the parent of y, they belong to the same parent or not. So finding the parent is just what I have told you initially. It is just a recursive function. If x is not equal to its parent, okay, so then we'll find out the parent of the value on parent of x. Okay, so we will find out the parent of x, and we will go on doing this until we find out a connection in which x is equal to parent of x, and thus the answer is the parent of x, which I have told you. We are iterating over this parent of x vector. And for joining, what we will do, because when we want to join two connections or two components, we will have to join their parents. So what we'll do, we'll first find out the parent of x and y, because these nodes we want to just join out their parents. So we want to find out, because if we want to join these two nodes, we want to go to their parents. So we will go to their parents, store the indices, and check that we have to join the one which has the smaller component size to the one which has the larger component size. And if x, like if the size of the x, the component of x which has a parent x is greater in size than the y, then what we'll do, we will make the parent of y, equal to x, which means that we are joining y to x, and will also increment the size of x because we have joined the whole component of y to x, and thus the size of the x increment, and same we will do for y. I hope you understand the whole concept and the logic for the union find. If you still have any doubts, please mention down. Thank you for watching this video. I'll see you in the next one. Keep coding. Bye.